let's start with natural language processing. And whenever you do natural language processing, you are going to be dealing with text. So your data is going to be in the form of text. And a text, you can think of it as a sequence of words or a sequence of characters. We are going to start thinking about natural language in terms of a sequence of words. At some point, we are going to switch and consider looking at sequences of characters. But already you're going to notice something. If you look at your text in the form of sequence of characters, you have very few characters, but at the same time, your sentences are going to end up being really long. N-A-T-U, and all of these is going to give you a sentence. So there is this trade-off. If you go with character level models, your sentences are going to become too long. If you go with word level models, your sentences are going to end up being reasonably long, but at the same time, your dictionary is going to grow. It's not like you have 32 characters anymore. You're going to have 1 million words in your corpus or even more. So there is this trade-off between word level and character level language models. We're going to start with word level. And the idea is that each word is going to get represented by something. You cannot just feeding natural language processing to a computer. It's not going to understand it. The computer understands numbers. It's going to understand 1, 2, 3, 4, 5, 6. At the same time, it can understand vectors or real valued vectors. And the idea of word representation is that you want to represent your words with vectors that convey meaning. You can represent this sentence by 1, 2, 3, 4, and 5. That's perfectly fine. But then if you want to compare 5 to 1, can you say that 5 is closer to 1? These two words, for instance, natural and representation are closer to each other? Or is the word word and representation are closer to each other? So there is no way for you to tell that because you're representing them with integers, 1, 2, 3, 4, 5, 6. In terms of meaning, you cannot say that 5 is any closer to 1 than to 2, because these are just integers. At the same time, you can just reshuffle your vocabulary and then associate a number 1 to representation and number 2 word and number 3 to language. So that's the idea. You want to somehow convey closeness. For instance, perhaps representations is closer to the word representation or is closer to the word represent compared to word. So that's the idea. And the idea is that you want to convey linguistic regularities in a continuous space word representation. What I just described with 1, 2, 3, 4, 5, 6 as integers, this is first of all discrete. Second of all, you are not going to observe any regularities when you represent your dictionary with just integers, your words with integers. There is another way of representing your words, and those are one-hot vectors. You create a dictionary out of your corpus. For instance, in this case, our corpus could be linguistic regularities in continuous space word representations. So you created a dictionary, and then you can say the first word in my dictionary is linguistic. The second word in my dictionary is regularities. The third word is in. This is the fourth one. This is the fifth one, sixth one, seventh one. Now you can associate integers to your vocabulary or words in your vocabulary. There is another way. You can say that the first word, I'm going to represent it by a vector that has a 1 value here and zeros everywhere else. So this is called one-hot encoding. So it's going to be a 1 here and zeros everywhere else. And in this case, because our vocabulary size was 1, 2, 3, 4, 5, 6, 7, you're going to have a 7-dimensional vector. The first word is, the first entry is 1. The rest of them are zeros. For regularities, the second one is a 1. The other ones are zeros. And this is called one-hot encoding, or 1 of k encoding, 1 of n encoding. In this case, 1 of 7 encoding. Again, this is discrete. You could have millions of words. In this case, we have 7 words in our dictionary. You could end up with millions of words in your dictionary. And this is going to end up being a huge waste of memory. You're representing a lot of zeros You don't need to represent them. Your vectors are 1 million dimensional and they are sparse. Most of the time, there is 0 except for one entry. And at the same time, there is no regularities. You cannot say that one word is closer to the other one. For instance, you cannot say that continuity is closer to continuous if you represent them by integers or by one-hot codes. So we are looking for a smarter way of doing it. And we are going to start with recurrent neural networks. To do that, it's a very old paper by today's standards, but it's at least going to give us a baseline to work with. What are you going to do? You're going to look at this sentence, for instance, linguistic regularities, etc. You start with linguistic. This is going to be a one-hot vector, 1, 0, 0, 0 everywhere. You start with a vector that is zeros. This is going to carry out your memory with you. At this point in time, at the first entry of the sentence, there is no memory, so we can just initialize that to 0. Then you're going to multiply that one-hot vector by a matrix. And as soon as you do that, you're picking out one of the columns of this matrix. This could be 1 million dimensional. In our case, it is 7 dimensional, but it could be 1 million dimensional. When you multiply it by a matrix, you can project into a lower dimensional space. For instance, the dimension of this ST could be around 100 or 256. So you're projecting a high dimensional vector into a lower dimensional one. These one-hot vectors could take only values of 1 and 0 to compensate for that and for you not to lose information when you project down. You're going to allow these entries to take values from negative infinity to positive infinity, or to take continuous values. And this is where this word continuous comes in. So it's going to give you a continuous space. This is low dimensional. You multiply it by a matrix that's going to carry the past with you. And then you're going to add these two vectors together. These are low dimensional vectors. You're going to do element-wise addition. And this is going to give you your word representations. This is nice because this matrix has the size of your vocabulary. Maybe your vocabulary is 1 million dimensions or 1 million words. This is going to be 1 million by 100 or by 256. And you're representing all of your words by vectors. How? If you're interested in the representation of the 100th word in your dictionary, you're going to read off the 100th vector from this view. And sometimes I'm confusing column with rows because it doesn't really matter. That depends on how you're going to code this in practice, whether you're multiplying your matrices by vectors from right to left. You're either picking a row or a column of this matrix. But it should be self-explanatory what we're doing. Now you're in a lower dimension, and your task is to predict the next word. So you're defining a task. Given linguistic and given the history, what is the next word? So you're going to multiply by a matrix B. This is going to take you from dimension 100 to 1 million. Out of these, you're going to get probabilities, or this is going to give you a probability distribution, telling you how likely is it that the next word is the first word in your dictionary. How likely is it that the next word in your sentence is the second word in your dictionary? How likely is it that the last word in your dictionary? And you have a lot of options here. One of them is the correct one, and you want to increase the likelihood of the correct one happening. And that's the role of training. Any questions about this recurrent language model so far? I'm going to write down the math exactly, and then you're going to know more details.
So I have a quick question. So the next word prediction, that's a probability distribution over the entire corpus, right?
Over the entire vocabulary.
And it's based on on a sentence basis. Your input will be like, what's the few words before that word?
Exactly. So now you want to go to the next word. Maybe you want to predict continuous. The good thing about carrying this memory with you is that you don't need to write a model that is going to look at linguistic regularity in. It's going to look at S, your history.
And the input data is structured in a way each time at each time iteration we send in the next word of that sentence.
So yeah, what is time here? Can somebody answer me? What is T representing?
It's the token position in the sentence, I'm guessing.
Exactly. So for linguistic, it is 1. For regularity, it is 2. For in, it is 3. For continuous, it is 4. This T here. And then you are always predicting the next word. Given the past, what is the future? And that is actually what is called language model. And then it's recurrent because you're carrying your history with you. Any
Yeah,
other
that makes
questions?
sense. Thank you.
What was the structure of SFT again?
What was
Or
this?
yeah, like the dimension of it, or like kind of like what that matrix would look like.
Yes. So this is 1 million dimensional. Let's call this 256 dimensional. This is going to end up being 256 dimensional. W is going to be 256 by 256. And U is going to be 1 million by 256. Does that answer your question?
Yeah, and I think you said you would kind of go over some of the math, correct?
Yes. So
Okay,
I'm going to
cool.
specify this exactly what
Cool.
we're doing. Okay, that was the figure. What is WT? It is just an index for any word that you choose. You know the corresponding between its integer representation, its ID, and the actual word. For instance, linguistic might end up being the 1026 entry of your vocabulary. You could either think of it as an integer, or you can think of it as a one of encoding. So you're going to have a vector. All of the terms are 0 except for 1026 entry. So that's WT. And this is 1 million dimensional. These are just as an example. That depends from corpus to corpus. Your vocabulary size might be different. But for now, let's pick 1 million to explain things. YT is going to give you a probability distribution over the next word. This one is also 1 million dimensional. Unlike WT, these are probabilities. So we need to write our model in such a way that the coordinates of these, as you add them up, are going to add up to 1. They are bigger than 0 because they are probabilities, and less than 1. So we need to make sure that this happens to them. So there is a question. What's your question?
I just wanted to clarify. So SFT is only carrying the history of their current sentence, correct? We're not using anything behind that?
Yes. So it's just the history, the current word. This is the history, the current word, and you're predicting the next word.
Okay.
Okay. Any other questions? Okay, perfect. So ST is going to carry our history with us. It's going to be low dimensional. WT and YT have high dimensions, the dimensionality of the vocabulary. This operation here using arrows, there is actually math behind it. You take WT, multiply it by a matrix. It's going to pick out one of the columns of this U matrix. So it's now basically the word representation, the vector representation of that word, plus a linear combination of the past history. Without nonlinearities, neural networks are going to end up being very boring. So this is going to be a nonlinearity, maybe a sigmoid function, a tanh function, the maximum of this term and 0. That's the ReLU function. Now you have the history here. You want to do your prediction. You multiply S by a matrix. That's going to take you from low dimension to high dimension, to the dimension of your vocabulary. Now this is the function G that is going to turn the output of this matrix vector multiplication into probabilities so that they add up to 1. It's a probability distribution. They are positive, the entries, and they're less than 1. So this is your nonlinearity, which in this case is just a sigmoid function. So this is an assignment for you. Just plot this and see how things look like. So this function is going to take values from negative infinity to positive infinity, and it's going to squash them from 0 to 1. This other one is going to make z's positive because of this exponential term. As soon as you divide by k goes over the entries here, and this is the size of your vocabulary. As soon as you divide by that term, they're going to end up being less than 1 because the numerator is less than the denominator, because the numerator is actually part of that summation and everybody is positive. So this has to be less than 1. And if you sum this over Zm, this is going to add up to 1 because the numerator is going to cancel with the denominator. And that's how you make sure that you get a probability distribution out. But we are not done yet. We are trying to optimize over these U, V, and W. Especially we are interested in this U because that's going to give us our word representations. We need to write down a loss function. And usually your loss function is going to come out of writing down a likelihood. You're doing maximum likelihood estimation. And as I mentioned, we are interested in U because each column of that is going to represent our words. Now you're turning your dictionary into a matrix. Now your computers can work with it. So what is going to be a loss function here before I explain the next one? Your loss function is going to be the one that is trying to maximize the probability of the correct next word. So the correct next word could be regularities. Regularities is the 9025 or 25th word in your dictionary. It means that you're going to pick out this output. You want to increase this value or the corresponding value to this entry, or you can actually take a log of that because it is equivalent. Maximizing the log of something is equivalent to maximizing that something. So you're going to try to maximize this. And this is nice because of this property that these values have to add up to 1. If you keep pulling one of these to the right, the other ones have to go down. They have to become less likely. So you're pulling one of these to the right, the other ones have to go down because they have to add up to 1. They are all positive. And this is the way that you are adjusting the parameters of your U. So from one step to the next step, you keep seeing data. This is one sentence in your data. You're going to see another sentence in your data, which could be this sentence here. You're going to see another sentence in your data, and you are basically memorizing your data. If I keep adjusting U, V, and W, how can I make the next word more likely? But let's assume that you optimize that. This is going to end up being an optimization procedure. You optimize for U. That's going to give you some word representations. How do you actually measure if what you learned is meaningful? This is one way of doing it. There are other ways of doing it as well. And we're going to solve these types of analogy tasks. A is to B as C is to what? For instance, family is to families as car is to what? And then your algorithm needs to tell you cars. Clothing to shirt is as dish to what? This actually has to be clothing. Is to dish, is to shirt as is dish to what? And your algorithm has to say both. You're going to create a data set like that just for testing your word representations. And this is one of the tasks that I'm going to assign to you. Go ahead, read the paper, find the corresponding data set, and then explore it. Your data set is going to be like this. Good to better is like rough to what? Good, best, rough to what? Better, best, rougher, what? Years, 2 years, law, and what? Okay? But how do you actually solve this task? Now you have word representations. You can represent the word A by the corresponding vector, the word B by the corresponding vector, the word C by the corresponding vector, any other word in your dictionary by a vector. And then you can use something like the vector offset method to solve this problem. How we're going to do it, you look at the vector representation for B, in this case, the vector representation for families, and all you are doing is reading off the corresponding column from this matrix. You are going to read off the word representation for A, or the vector representation for it, subtract, and then add the word representation for C. And your task is go in your vocabulary, go one word after another one. Each one of them is going to have the corresponding vector representation. And look at the cosine similarity between this vector and the other vector. So one of them is coming out of a bunch of subtractions and additions. The other one is coming out of the representation for each word that you're considering. There is going to be an angle between them, and this is the cosine of the angle between the two. And this is a measure of the similarity between these two vectors. Now that you have vectors, you can compare their similarities. How similar are they? And you find a word that is the most similar to these operations. And that word your algorithm is going to report here. It might end up being correct. It might end up being wrong. Most of the times it's going to end up being correct because it's a statistical method. And then you're going to count the number of times that it was correct and report it. And this way you are encoding meaning in your algorithm. Let's actually see it. Why does this vector offset method work? You start with this observation that if you take the vector representation for man, uncle, and king, add the same constant to all of them, And by constant here, I mean a vector of the same dimension. If your vector representation for man, uncle, and king are 256 dimensional, you're adding the same vector, it's the same offset to all three of them. And then it's turning a man to a woman. It's turning uncle to aunt. And it's turning king to queen. And this is how you're encoding meaning in the space of words. Or similarly, let's pick this king, queen. If you add another constant to king and queen, that one is gonna make these words prolong. It's gonna turn queen to queens, king to kings. So this offset method works. You subtract, add xc, and then you look for the word that is the closest. Now let's see whether this was for one example. Let's take a look at the entire data set. Did we actually learn something? This AD is the dimension of this hidden space, where it's actually the dimension of U. As you keep increasing it, you are getting better and better at solving the task of syntactic similarities. So it is conveying the message that higher dimensions or high dimensional word vectors are important. And it makes sense. If you project something that is high dimensional to only the real line, one dimension, you're going to lose a lot of information. So the higher dimension you keep for ST, the better it is. And this is the number of times that the algorithm is correct. And you see it's not perfect, but the fact that you are learning something out of this exercise is really interesting. The other one is semantic regularities, like what you have here. Clothing to shirt is similar to dish to what. And then you have a data set of that. Then here you have a different metric. This metric is no longer used, so I don't want to spend too much time on it. You can actually look at the Wikipedia page. It has a formula 1 minus something divided by n times n minus 1. N is the size of your data. In that formula, you're going to see some d's, and those d's are these distances. This Spearman's rho is going to give you a number from -1 to 1. If it is 0, there is no correlation between what you're reporting and the word representation of the word, the correct word, the one that you're looking at. If it's 1, there is higher correlation. If it's -1, these are actually anti-correlated. So the higher is the better here. Again, this accuracy is no longer used. So we are going to work with more modern metrics in the next slides. Any questions about this paper? Was everything clear?
When you speak of the dimension, is that the embedding vector's dimension?
Exactly. So it's the dimension of S.
Thank you.
Any other questions? The question on the chat is, are you training U, V, W? Exactly. So you're going to be training U, V, and W simultaneously. You're going to write down an objective function, which is the log of the likelihood or the negative of the log of the likelihood, and you're trying to minimize that. What are you trying to adjust from one iteration to the next iteration of your optimizer? You're optimizing over U, W, and V. And these are shared. It is going to be the same U, the same V, the same W when you are predicting the next words. And it's this idea of parameter sharing that's coming into play again. So recurrent neural networks are parameter efficient in that sense. Does that answer your question? Okay, perfect.